Okay, the first student will be Siti No. Is Siti here?
Yes, doctor.
Yeah, you just go ahead and share your screen.
Okay. Should I start now?
Yeah, sure. Go ahead.
Okay. Okay. So for question number 1, let the random variable xn have this distribution function fnx to show that Sn converges in distribution to x, where x is an exponential random variable with mean 1. So first thing, we need to show that the limit and the limit fnx and approach infinity is equal to fx. So we will get the fx is 1 minus exponent negative x. So the probability density function of x is obtained by taking the derivative of the fx, which gives this PDF of an exponential random variable with mean 1. That's all.
Okay. Yeah. So let me just annotate this one. So yeah, this part here is important. Yeah, because you are making use of this result in calculus. Very important result. So basically, this is just you just replace your x with minus x, right?
Yeah.
So you get this. Okay. And basically, yeah. So this is a distribution function. So you just need to take the derivative, right, to show that it's to find its PDF. Okay, good. Okay, thank you. Okay, next student, Fadila. Is Fadila here?
She is still on her way, doctor, to
Okay,
came into Zoom.
we start with other questions first. Yeah. We work with question 3. I know.
Hello.
Yeah, I know. You can share your screen.
Hello, doctor. Can you hear me?
Yeah, we can hear you.
So this is problem 3. So we need to show that the function will converge in probability to mean squared. So first I do expectation on the equation. Then I got 1 over n choose 2 ex1 x2 plus ex2 x3. Then ex1 times ex2 will become mu squared. Then by using the formula that Dr. teaches before, mu squared plus delta dot will become n choose 2 times mu squared. So I just cut n choose 2 and n choose 2, then become mu squared. So this is the expectation of the function. So next, I search for the variance of xi, xj. Then I've got theta squared plus 2 theta mu squared. Then I do variance on all the function. So it becomes 2 theta squared plus 2 theta mu squared over n minus 1. After that, I do Chebyshev inequality. Then I insert all the function that I already searched for. Then got as n approach to infinity, 2 theta squared plus 2 theta mu squared over epsilon and n minus 1 will become 0. Therefore, the function summation of I less than 0 xi x 0 over n choose 2 will converge in probability to mu squared. That's all.
Okay, thank you. Can you scroll a bit up?
Okay.
Yeah, just go through. Okay, so yeah, so we want to show. Okay, just a minute. Yeah. Annotate. strange. I can't annotate this time. Just a minute, yeah.
Okay. We need to show that SIT converges to mean squared, right?
I'm trying to write something on the screen, but it seems like for your screen I can't write anything. Like just I don't know. Maybe you're using is this a handphone, right?
No, iPad.
Oh, iPad. All right. Okay. Okay. Not sure. Yeah. Maybe there are some restrictions. Okay. So over here, yeah. So first we want to show that convergence in probability. So we want to show that the probability that this term, right, sum of xi xj divided by n choose 2 minus mu square, right, the absolute of it greater than or equals to epsilon, that probability converges to 0, right? So the first thing, so we know that generally we're going to use Chebyshev to do this, okay? Because the form is actually so the thing that I want to prove is actually the left hand side of the Chebyshev inequality. But then we got to make sure that the mu square here is the expectation, right? Because Chebyshev's inequality says that it is the expectation, right? So we have to demonstrate that first, right? Can you scroll up again? Yeah. Okay, correct. Yeah, that's what you. Okay, just now you scroll down, right? Can you scroll down? Yeah. Okay, so this is what we wanted to show, right? Okay, the purple one. Okay, so then we check the expectation, all right? Can you scroll up again? So therefore you check the expectation, right? Now this expectation is not hard to check because the sum of I less than j simply means that you have 1, 2, 1, 3, 1, 2, 1, 3, 1, 4 until 1n, right? Then 2, 3, 2, 4 until 2n, right? It's basically half the upper triangle, okay? Because whether you compare xi, xj or xj, xi, they are the same because it's a product, right? So it doesn't matter the order of multiplication. And therefore you basically, because they are IID, so basically you are just trying to count how many of them are there. And basically this is just counting the upper half triangle, all right? The number of elements in the upper half triangle is basically easy to find. Is once you know the geometry, this is very easy, right? It's basically n square. N square is the whole thing. You delete the diagonal, right? So because those are the x1 square, x2 square, right? You don't want that. And then you half it because it's only half of it, right? So basically that's n choose 2, right? So then you show that this is mu square, and therefore you can straight away use Chebyshev's inequality. All right. So you can just scroll down. Okay. Then after that, you basically need to find the variance of that that term, right? The sum xi xj, right? Divided by n choose 2. So since this is IID, so you first find the variance of one of the term, right? So okay, so that will be by definition, all right? You get the first line, the second line. I think in the second line you can simplify your work because your second line is basically just expectation of xi squared times the expectation of xj squared because they are independent, right? Of course, you want to use the method that you use is also okay. But you get the same thing, right? You can just directly work on it. But you get the same thing. That's what I wanted to say. Okay. Then therefore, therefore your variance is basically just all right. Okay, so it's correctly done because they are n choose 2 terms. So you cancel off one of the terms in n choose 2. Okay, and then basically That's it. So basically, after that, your numerator is related to n, but your denominator is related to n, but your numerator is a constant, right? So therefore, as n tends to infinity, this will basically just go to 0, and then you show the result. Okay. All right. Okay. So yeah, so convergence in probability is generally not a hard. It's generally considered an easy problem because you already know like you're going to work with the Chebyshev. Okay. All right. Okay. Thank you.
Thank you, Doctor.
Okay. And okay. Okay. So Fadila is here already. So Fadila, can you share screen?
Yes. Okay, can everyone see my screen?
Yeah, we can.
So basically question 2 asks us to show that xn converge to in distribution to a random variable x with distribution function fx equal to exponential to the power of -1 over x. By using the definitions of conversion in distribution, xn converge to a random variable x in the distribution if and only if limit n to infinity function of xn is equal to function of x. So now we need to find the limit of f and x, but the limit leads to the indeterminate form. So we apply L'Hopital's rule and we find the limit of ln f and x, and we get that the limit n to infinity is equal to -1 over x, -1 over x. So limit n to infinity f and x is equal to exponential -1 over x, which equal to fx. So that's it.
Okay. Okay, scroll a bit up. Okay. Yeah. You say that you apply L'Hopital's rule, right?
Yeah.
Is the condition? Is there a condition to apply it here? You see here, if your n tends to infinity, this term will go to 0, right?
Okay.
So basically, then you have a case of 1 power of n where n tends to infinity. So is that the usual condition for L'Hopital's using L'Hopital's rule?
Yes, because I get that the limit here leads to the indeterminate form 1 to the power of infinity. So I apply the
1 to the power of infinity, but is that one of the condition? I thought L'Hopital's rule is only something like that.
I'm not sure.
1 power of infinity. Well, if you have 1, you raise to power of anything is still 1, right?
Okay.
So I think the argument to use apply L'Hopital's rule is okay. Let me see how you can. It's a little bit it's not watertight. Let me see. If you write it like this, 1 plus nx minus 1. So yeah. So basically, you will still have. Let's argue like this. If you want to argue your L'Hopital's case, you can argue like this. So basically, this one your xn you can take out, so your nn, and you have this, right? Then basically you argue that this is going to infinity, this is going to infinity lah. Okay. So you have this case. You can do this, right? Okay.
Okay.
Now, so I mean, like this argument is a little bit doubtful, right? You rearrange it and you can get. However, although this works, but it is actually in the, yeah, it is kind of like taking a long way to the end. So actually, you can basically just argue like this, right? So this term here, right, 1 minus 1 over 1 plus nx power n is basically 1 minus 1 over nx n, okay, when n is large, right? When your n is very large, you add 1, it doesn't matter, right? Okay?
Yeah.
Yeah, it doesn't matter. So here you can further note that this will be 1 minus, you can write it like 1 over x over like, okay? All right?
Oh, okay, doctor.
So once you have this, then it's very clear already, right? Because this is the classic form for you take limit of this, then it's very clear that this should be e of minus 1 over x. Okay? So yeah, make an argument. So sometimes this kind of mechanical way, they kind of like, yeah, since you know that, okay, so there's this L'Hopital's rule, so we just try to make it into the form of L'Hopital, then we kind of like can apply the machinery and then we are done, right? But sometimes there are actually easier ways, and which may not be very well, which requires a bit of thinking. Because sometimes easy things are easy to miss, right? Because they seem too easy, right? So here, so take note that when you have something 1 plus nx, when your n is large, this 1 doesn't matter. Because once this 1 is removed, then things become clearer. Then you suddenly see that, oh, this is something similar to your the limit result for exponential exponential of x. Okay, so with this term change, then it becomes easy. Yeah. Okay.
Yeah, I understand, doctor.
Okay. Thank you. Okay. Then for question 4, let's is Nabiha here?
Yes.
Okay.
Can you see my screen?
Yeah.
Okay. So the question gives us the expectation of yn approaches a and the variance of yn approaches 0 as n goes to infinity. And then the question asks to prove the probability of yn minus a more than or equals to epsilon approaches 0 as n goes to infinity for some epsilon more than 0. So I let from here, I let the absolute of expectation of yn minus a less than epsilon over 2. So since epsilon is more than 0, when we rearrange this, we will get a is more than expectation of yn minus epsilon over 2. Then the probability of yn minus a more than or equals to epsilon is bounded by the probability of yn minus expectation of yn more than epsilon over 2. And then we apply the Chebyshev inequality. So this thing is bounded by the variance of yn over epsilon over 2 squared. So as the question gives us the variance of yn approaches 0 as n goes to infinity, then this thing will also approaches 0 as n goes to infinity.
Okay.
So
I didn't use the hint given in the question.
Just a small, okay, so let me see. These, I'm trying to see the connection between this part and this part.
So isn't it?
So you have this, but why would this imply this statement?
So isn't it? I replace this thing with this one.
You replace, but this thing here has an absolute. So
Oh.
So basically, is this step here is not convincing. You say a larger than this, but okay, this is just relating a with these quantities. How do we know that this probability is therefore bounded by this?
So I think this
will,
step is
at
shouldn't
most
be
it
there.
will involve some kind of rearrangement here. But once you have the rearrangement, why would I know that the left hand side is less than or equals to the right hand side? So it's mysterious, right?
So I think, yeah, this thing shouldn't be here, right?
I think the problem is this part is unclear. How would this probability be less than or be bounded by this part? It is unclear. On what basis do you bound it?
Because I think this one came from the expectation of yn. So this two here is basically come from here too. So one thing is bounded by this two thing. Then I just move the two here.
Okay, I think that okay. So this part has some problems. All right. It's okay. Then let me show you how to argue this part. Okay.
Should I stop sharing?
Yeah. Okay. Thank you. Just stop sharing. Okay. Okay. Can you see my screen?
Yes.
Okay. So I'm just going to go through this. Let me annotate. Right. Okay. Let's see. All right. So first thing, because we're going to use Chebyshev's inequality, yeah. Okay. So now, first thing we note the following: my yn subtract a. Okay. I can write it like this. Now you notice this part here. This is the add zero trick. You introduce something and then you cancel it off, right? Introduce and cancel, right? So basically, you're not doing anything funny here, right? You just add something, you remove it, but then you in this case, after you add and remove, right, you make a rearrangement, right? So you have one grouping here and one grouping here, okay? So this grouping is what you actually are familiar with. This will allow you to use Chebyshev's inequality because this is yn and minus its expectation, right? And over here, this is the triangle inequality. Okay, you have absolute A plus B is less than or equals to absolute A plus absolute B, right? Remember at the beginning of the course, we had a few examples of using triangle inequality. This triangle inequality is considered an elementary inequality in analysis, right? So you should always remember it. Sometimes when you try to work with these kind of problems, it's useful. It's It's a simple inequality, especially when you want to deal with absolutes of sums. Then you should immediately recall that this inequality may be useful. So then I know that, okay, so now I can write it as two parts, right? Okay. Right. And therefore, if you have epsilon greater than 0, so basically this statement here, right? Okay. This implies that since your yn is this, right? So it implies that so okay, so here maybe I write it if you write it like this, okay? Okay, so yn minus a greater than or equals to epsilon implies that because this guy is bounded by this guy, right? So therefore it means that this upper bound is also larger than or equals to epsilon, okay?
Okay.
Right, because your yn minus a absolute is larger than epsilon, and there's some guy larger than it. So this guy that's larger than it must also be larger than or equals to epsilon, right? So this is okay. And from here, you rearrange, you get this, okay? It's basically just moving it around. Right? Okay, then you have if n is sufficiently large, such that this is less than 2, okay? So let's consider the case when your n is sufficiently large. So let's say my n is large enough such that this expectation minus a, right, is bounded by epsilon over 2. Okay? Then, okay, equivalently, when you put a negative sign in front, so it will flip this inequality sign, right? So the negative will go there, okay? And therefore, right, what you want to do is, because you want to work with this part, right? Therefore, so this is epsilon minus this e. So less than or equals to epsilon. So we want something that is less than or greater than this thing, right? So we got it here. So plus minus epsilon over 2, that gives you your epsilon over 2, okay? So once you have got this part, then you apply your Chebyshev. So you have this your Chebyshev, right? So this is what we want, right? Then we write it in the form of this is my Chebyshev. Here directly you can't use Chebyshev because your A is not expectation of Yn. But you manage to have an equivalent form here, right? So then you have, so this is equal to this form here, okay? And from here you apply your Chebyshev, okay? Right, so then by hypothesis, your variance of Yn tends to 0. So this proof is complete. Okay, so the idea here is you have to, from here, this is what we have, right? But we want to rearrange it in a way that allows us to apply Chebyshev's result, right? Which means you got to rearrange you got to somehow get rid of this A and replace it with E of X, Yn. So these are the sequence, okay, sequences that lead to this replacement. Okay, so basically here it doesn't matter. So what you might be wondering, why do I have to choose epsilon over 2? It doesn't really matter. It could be just anything, right? It could be any value here. It's just that it's easy to do because over here you have epsilon minus something, right? Of course, if you have used epsilon over 6, epsilon over 10, it would have worked anyway, right? It's just something, as long as this thing is not epsilon, it's okay. Just choose it so that it's something smaller, yeah, smaller than epsilon, right? Then it will work. So it doesn't really matter here, okay? Because this part, if you have epsilon over 3, then basically this factor becomes a 9, right? So it still doesn't affect the convergence, because the convergence is determined by variance of Yn. Okay.
Okay, I understand now.
Okay. This result is useful. This you can later use this theorem to, for example, let's say if you want to show convergence, right? Show that yn minus something a converges in probability to sorry. So you say yn converges in probability to let's say mu. Sorry, this, let me see. This converges in probability to a. Sorry, yeah. Okay. Now in this case, your a need not be your mean, yeah. Okay. So it can be something that's more general. Okay. Generally, the usual case is this is a mean, right? But it need not actually be a mean. It can be some particular constant. Okay, and you can invoke this this result, this question 5, the theorem in question 5. But of course, there's a condition, right? The condition is that the expectation of your yn must what's the condition?
Approaches A.
Yeah, it has to converge to A. Okay, and the variance of yn has to converge to 0.
Okay.
Because sometimes, you know why? Because sometimes your expectation of yn, right? It is not exactly equal to the parameter. It may be something like this. Yeah, maybe something like this. Okay, this means that your yn, right, is biased. It's a biased estimator of your a. Okay, so well, a is your actually your a is your okay, a is your mean, a is your is the model parameter lah. Model location parameter. Okay. Okay, so not all the time you have expectation of yn equals to the location parameter, yeah, because sometimes there's a factor that depends on n, right? And this happens if your particular yn is actually a biased estimator. But of course, you know that in the limit, this will tend to a, right? So so you can't actually directly apply Chebyshev, but you can invoke this result, right? You just show that, hey, you know, my expectation of yn, although it is not a, but it converges to a, so this is satisfied. And then you can calculate the variance of yn. If you can also show that it converges to 0, then you can invoke that result. Yeah. Okay, this is actually allowed. Because you don't have to work out all this. You don't have to work out all this proof here. Okay, you can just apply this result. Yeah, if there's a need to use it. Okay.
Okay.
Okay. Thank you.
Thank you, Doctor.
So the next person is Aishwarya.
Yes, Doctor.
Yeah.
Can you see my screen, Doctor?
Yeah, I can.
Yeah, all right. So for question 5, it is given that xi be independent and identically distributed normal random variables with mean 0 and variance sigma square. Denote the sample mean as xn bar. Show that 1 over n, the summation of xi minus xn bar square converges to sigma square. Then this is the question you can apply the theorem in question for. Which version of the law of large numbers are you using? So we know that xi follows normal distribution with mean 0 and variance sigma square, and xn bar follows n as well with mean 0 and variance sigma square over n. So I take this term over here and I simplify it as below. So I expanded the square, and here I substituted the summation of xi with nx and xn bar, and then I simplify it to be so. And then from here, I said, first of all, I showed that this converges in probability to sigma square. So I used the Chebyshev's inequality, and then I showed that this approaches 0 as n approaches infinity. So the limit when n approaches infinity for the probability of this function is equals to 0. So I said that 1 over n summation of xi square converges in probability to the expected value of 1 over n, the summation of xi square. So it is equals to sigma square. And for the next one, I said that the xn bar converges in probability to 0. Again, I used the same Chebyshev's inequality, and I showed that this approaches to 0 as n approaches to infinity. So the limit of this probability is equals to 0. So the xn bar converges in probability to the expected value of xn bar, which is equals to 0. So by A and B, I said that 1 over n, the summation of xi minus xn bar square converges in probability to sigma square. So this is basically the weak law of large numbers. I'm not sure if my argument is right, but yeah.
Okay. Okay. So basically, you're applying the weak law of large numbers, because if you are using Chebyshev, then it's the weak law, right?
Yeah.
Which version of the okay, the first thing is you check the expectation. So it says, okay, it asks you to use the previous result, right?
Yeah.
So the previous result is saying that if expectation of yn converges to a, and the variance of yn converges to 0, then this thing here converges to 0, right?
Mm-hmm.
This is the previous result. So if you want to use the previous result, then we show a few things, yeah? So first we show expectation of yn, right? Does it converge to sigma square? So let us see, yeah? So let's say this is our yn, right?
Mm-hmm.
Okay. So what is its expectation? So you do something like this. If you do expectation of yn, you get Because this will be just 1 over n times summation expectation of this. So basically this IID, so basically you have expectation of x1 minus this. Right. And your x n bar is basically the mean. Right? So what happens here? So if your n tends to infinity, your xn will tend to mu, right? All right.
Yeah. Mm-hmm.
As n tends to infinity, your sample mean will converge to the
Converge to
population
mean.
mean, right?
Mm-hmm. Yeah.
Which is 0, right?
Yes.
So meaning that this will converge to expectation of x1 square, right?
Yep.
Agree?
Yeah, I agree.
Okay, simply because this guy will converge to 0, so then
yeah.
this will be, yeah. And this will be basically just the variance of x1 plus the sum, right? Which basically is
Equals to the sigma square.
basically sigma square, right?
Yeah.
Because this is 0. Okay. So yeah, condition 1 we show it already. Okay.
Mm-hmm.
Okay. So we got condition 1. Then so we got this already. Then we check this result, right? We check that the variance of yn converges to 0. Okay. Then because once this is done, we can then apply this result and we will get our weak law of large numbers, right?
Mm-hmm.
Now, so then we need to show this step. What do you do? Can you scroll down? Okay, so so it seems like, okay, this part, yeah. No, okay, so yeah, we cannot do it like this because simply because this part here is actually okay, you want to show the variance of yn, which is the variance of 1 over n sum xi minus x bar square. Right?
Mm-hmm.
So this is basically 1 over n. This n squared, but then since you're summing IID, so basically you have one variance of x1 minus x bar squared. Okay. So I got this. So then we want to okay. So then over here, what happens if your xn, so of course your xn bar will tend to 0, right? As n
Yeah.
tends to infinity, right?
Mm-hmm.
So basically this will tend to 0, right? Because so this guy is tending to 0. So then at the end in the limit, your numerator will be variance of x1, right? Square.
Yeah.
Then divide by n, right? So this will tend to, of course, 0, right? Okay.
Mm-hmm.
So basically, these two conditions are fulfilled. Then you apply. So this is a bit unnecessary kind of expansion. So you basically just need to use the notation yn.
Okay, doctor.
So you just say that you check those two conditions okay already. Then directly your so your a in this case is what, 0, isn't it?
Yes, 0.
Okay. It's bound it well, you don't even need this. You can just invoke the result, say that this is equal to 0. Okay.
Yes. Okay, doctor.
Okay, thanks, Aishwarya.
Thank you, doctor.
Okay, then we have question 6 from Farah.
Okay, can you see my screen, doctor?
Yes.
Okay. So for question 6, we need to prove Poisson's theorem if AI, where I equals to 1 and 2 are independent events, and P n bar equals to the summation of I equals to 1 until n of probability of AI over n, and Sn equals to the summation of I until n of the indicator function AI. Then Sn over n minus Pn bar will converge in probability to 0. So here we can see that the Pn bar equals to this quantity is equal to the expectation of Sn over n for epsilon greater than 0. Hence, by using Chebyshev's inequality, we will this probability over here, this is less than equals to the expectation of the absolute Sn over n minus Pn bar square over epsilon square. And then here we recognize the numerator as the variance. So from the question, we substitute Sn into this quantity, and then we do the expansion for the variance. And so towards the end of the computation, we will get 1 over 4 because the at most the probability of deviating from the mean is 1 over 4. Hence, 1 over 4 n square epsilon square approach 0.
Okay. Yeah, the reasoning is correct. Let's scroll up again. Scroll up. Okay. First, so first make this observation, right? Yeah. Because this observation will allow you to apply Chebyshev's inequality, isn't it? Yeah. By noting that this quantity here, Pn bar, is basically the expectation of Sn over n. Yeah. Okay. Please take note, the expectation of an indicator function, right, is equal to PAI. This very important result relating indicator function and the probability through expectation. This is basically just your Bernoulli case, because when AI is happening, it is 1. it happens with probability PAI. When AI is not happening, so it's 0 times PAI complement, right? But so you ignore this part. So basically, it is this result. This is a simple result, but it is very useful in probability work, right? So you should always keep this in mind. So once you have this, yeah, apply Chebyshev, right? And then over here, so you make use of the definition, right? So then you have this, right? And can you go down? Okay. Okay. So once you are here, basically this one you apply definition, all right? So this one, I square basically is just 1 square. So basically you still get this thing. And here this is a sum, right? This is the product. So then you have this. And then you know that since your P, this is a probability, right? You have a probability times itself. It cannot go out of 1 over 4. Okay? This is a basic inequality. It cannot go out of 4. Anybody knows why? It cannot go out of 1 over 4. This is also considered a basic inequality. Anybody wants to explain? Farah, why is it bounded by 1 over 4? How do we know it's bounded by 1 over 4? Farah?
For this one, I'm not so sure, Doctor, because when I look for the Poisson's theorem, I just figure out that the most is the probability can go as 1 over 4.
Okay, you can think a little bit about it, right? So why would this not escape? Why would this not go out of 1 over 4? Let's think of it. Since I emphasize a lot on geometry, right? There are several ways you can find out that it's not going out of 1 over 4. Just do some basic things, you will know it. What's the most basic thing you can do here? Okay, how does it look like? If you graph your function here against P, how would it look like? What do you notice about this function? Is it a linear function? What function is it? Anybody wants to help? What function is this?
Uh, can we differentiate this equation, then like find the maximum, then?
Yeah, sure. We come to that later. Later, I want to develop your geometrical intuition, right? So later you will see why that suggestion you make is correct. But what is this function?
Quadratic function.
Huh?
Quadratic function.
Yeah. Is this your elementary quadratic function, right? Okay. So quadratic function, this is the factorized form. This is the, well, I just expand this so that in case you can't see the 2 here. So okay, quadratic. So where are its roots? Where are the roots of this quadratic function? From here, you know the roots, right? Where are the roots?
0 and 1.
Okay, clearly 0 and 1, right? Okay. So you know this quadratic function will pass through these 2 points, right? Okay. So your quadratic function is either going up like this or coming down like this, right? Which case? Going up or coming down?
Going up.
Going up, why?
Because the coefficient for the
yeah, this thing you learn in high school. Okay. Actually, you can so this part here, if the coefficient is negative, it's going up. Otherwise coming down, yeah. So you know that it's going up, right? And by okay, there are several ways to do this by a symmetrical argument, right? Your quadratic function is symmetric around its maximum point. Okay, so you know that the root is 0 and 1 and is symmetric around the maximum point. So the maximum point has got to be at 1/2 lah, correct? Because other points it cannot be symmetric already, right? Because your roots are 0 and 1, right? So this implies that its maximum has to occur at p equals to 1/2. And when your p is equal to 1/2, what is this value here? 1/4 lah, right? Correct?
Yes.
Therefore, is it not clear that p times this is bounded by 1/4, right? Because your whole curve, right, is below this line. It will touch this 1/4 line at the point when p is equal to 1/2. Okay, that's why these things are, if you develop your geometrical intuition, these kind of things are easy to get. Okay, if you don't develop the geometrical intuition, it looks like very mysterious, right? It is actually not mysterious. Okay, so that's what I've been also trying to develop, yeah, as we learn these things. Now then, going back to the idea of using differentiation. Okay, of course, if you differentiate this thing, you will take the derivative, right? You basically is you get what? You get 1 here, you get -2p, right? So you set this to 0, then p equals to 1/2. Basically, if you use derivative, you are basically just trying to find this the position of this stationary point, right? Okay, because at this point the derivative is flat, right? So the derivative is 0. So that's your maximum point, and it occurs at p equals to 1/2. Okay, that's also okay, but it all comes from this graph, yeah. Okay, so I just want to connect the two things together, right? If you use this graph, you don't need to use derivative. It's very clear already. In fact, someone who has not studied any calculus, they will not be able to do this. Okay, if someone, let's say a high school student, like maybe just Form 1 or even Standard 6, they don't know how to do calculus. But if they know some graphing, right, they can deduce this result. Okay, so those are kind of like very talented students are very young already. Why can they find? They will probably figure this out on their own, because they don't need to rely on this thing. They just basically rely on the basic principles of graphing, right? So because these things can be learned, right? So it's not. It's just that some people are more sensitive to this kind of approach. Okay. Okay, but again, all these things can be learned. Okay, it's not a big deal. All right. Okay, so that's what I wanted to say. Why this is 1/4. Yeah. Okay. Anyway, let's go back to here. So okay, this is 1/4 is bounded by 1/4. Okay, correct. But this one is a constant, so you can take out. But you sum one n times, so there is an n here, right? Farah?
Okay, I forgot about that one.
Of course, it doesn't affect your result because since it doesn't affect, but just for completeness, so this will cancel with one of the n's. Okay. So yeah, okay. So this is so you show the proof already, right? Convergence and probability. Okay. For this case. Okay. Thank you, Farah.
Great, thank you, Doctor.
Okay. So as we do the tutorials, we learn some extra things, and those things usually in the solutions we just talk about the solution, right? We don't talk about these side things. Like for example, in the solutions, I'll just mention p times 1 minus p is bounded by 1/4, right? But if we have a session like this, then I can explain more why that bound is used. Okay. Okay. So that's tutorial 7, and tutorial 8 has the final one has been posted. So let's take a look. Tutorial 8 in the spectrum. Okay, so this is tutorial 8 in spectrum. One question on the Lindeberg-Lyapunov condition, and then the rest will be some exercises in using characteristic function, right? Okay. So this will be the last one, and we will talk about it next week, right? Next Thursday, right? So this one, Lindeberg-Lyapunov must know. I'll definitely ask this question about either one of these two things. So you need to at least develop some familiarity with this, how to use these conditions, right? So here's a chance to do some exercise. Okay, anyone wants to volunteer for this question? Especially those who have not done any questions. There are a few students who have been avoiding doing questions. I don't know. It's for your own benefit. Yeah. If you volunteer to do these things, you go through the process. Even though it might be wrong, right? But then you will understand why you are wrong. So it helps a lot. Yeah. So yeah. For your own good, you should volunteer yourself. Ida wants to try question 2. Okay. Question 2 is basically just finding some exercise in working with the characteristic function. Is Huawei Ken here? Huawei Ken. Yeah. So you want to try some of the questions? Okay, number 1, yeah. Wow. Anyone else? Three more questions. And after that, we can just stop earlier today. Yeah. Shirley Chan here. Shirley. How about Dina? Dina, you want to try a question?
Try number 3.
Dina, you try 3, yeah? Okay, 2 more questions. Then, so once we get the volunteers, we finish off. Yeah. Eugene, question 4. Okay. Last question. Atira Nudra. Here, are you here? Or Albert P. Albert here? Oh, Shirley, you want to try question 5? Okay. So you do question 5, Shirley. All right. Okay. So yeah. So that's all for today's tutorial. Right. Okay. So any more questions from you? And then any more questions? Otherwise, we can stop earlier today. Yeah.
No question, Dr. So far.
Yeah. Tutorial 8 is on Thursday. So next week, we'll do some revision with you on Tuesday, right? Okay. So then that's all for today. Last year of 2020. Yeah. So wish everyone a new year. Okay, so that's all.
Happy New Year, Doctor.
Yeah, Happy New Year to everyone.
Happy New Year.
Yeah. Thank you. I'm ending the meeting now. Yeah. Happy
Thank you,
New Year,
Doctor.
everyone. Okay. Bye bye.
Thank you, Doctor.